Okay, now I'm going to show you how to go back and forth between rectangular form and polar form when we're looking at coordinates. So something that you need to know in order to do this is that x is equal to r times cosine of the angle and y is equal to r times sine the angle. And one more thing that you need to know is that x squared plus y squared is equal to r squared. Now, we've seen this before when we talked about the unit circle, but with the unit circle, the radius is 1. So with the unit circle, you would have x squared plus y squared is equal to 1 squared, which is just 1. And this is going to help us go back and forth between rectangular and polar. Okay, in parts A, B, C, and D of this first example, we're starting in polar coordinates, and I want to change this to rectangular coordinates. Now, no matter what form we're looking at, it should still be the same point on the graph. Once we change this from polar coordinates to rectangular coordinates, we're going to plot both of them and make sure they're in the same spot when we overlap the xy plane and the polar plane. So to find my x coordinate, right now we're in polar coordinates, so we have r in our angle. So I want to change this to xy form into rectangular coordinates. So to find my x coordinate, I'm going to take my r times cosine of the angle. So my r is 3 times cosine of pi. Cosine of pi is -1, and when I take -1 times 3, that gives me a -3. Y is 3 times sine of the angle, which is pi. Sine of pi is 0, and 0 times 3 is 0. So my rectangular points that correspond to the polar point 3 pi should be -3, 0. So when I look at this, let's plot the polar point first. They should land in the same spot, whether it's rectangular or in polar form. They're just written in two different forms, just like 1/2 and 0.5 are the same thing, but they're written different ways. If I open up an angle of pi, so I'm going to sweep open pi radians, and then I'm going to come out 1, 2, 3, and I'm going to plot that point. That is if I'm plotting the polar coordinate. Now, if I'm plotting the point -3, 0, I would come out 1, 2, 3 in the negative direction, and I wouldn't move any vertical distance. And as you can see, I land in the same spot. So these 2 points, -3, 0 and 3 pi, are the same point. They're just written in 2 different forms. So you can always go back and verify it by plotting it and making sure that they're in the same place on the xy plane or on the polar coordinate plane. So for part B, it's in polar form because I have my r and my theta, and I want to find it in terms of x and y. So to find my x, I take r times cosine of pi over 3. Cosine of pi over 3 is 1/2, and when I take 1/2 times 2, that gives me 1. Y is going to be 2 times sine of pi over 3, and sine of pi over 3 is the square root of 3 over 2, and when I multiply that by 2, I just get the square root of 3. So the point in polar form is 2 pi over 3, and then the point in rectangular form, when I write it in terms of x's and y's, is 1 square root of 3. Part C, I take my value of r, which is -10, times cosine of pi over 6 to find my x value. At pi over 6, my cosine is the square root of 3 over 2. And when I multiply that by negative 10, I get negative 5 times the square root of 3. My y value is going to be negative 10 times the sine of pi over 6. And the sine of pi over 6 is 1/2. And when I multiply that by negative 10, I get negative 5. So written in polar form, my point is negative 10 and pi over 6. Written in rectangular coordinates, it's negative 5 square root of 3 and negative 5. Last example, this is written as polar form in r theta form. So to find my x, I take my value of r times cosine of pi over 2. Cosine of pi over 2 is 0, and 0 times negative 4 is 0. Y would be negative 4 times sine of pi over 2. Sine of pi over 2 is 1, and 1 times negative 4 is negative 4. So when I write this in terms of x and y, my point is going to be 0, 4. Okay, in the next 4 examples, parts A through D, we're going to work in the other direction where it's given to us in rectangular form, and we want to change it to polar coordinate form. So right now we have it in the form xy, and we want to find the radius and the angle that we would sweep open in order to get that point. So the first thing you should do when you're looking at rectangular points and you're trying to change it to polar coordinate, you want to make sure that you have the correct angle that matches with the corresponding quadrant. So if you notice, this point, if we plot that on the xy plane, because they're both positive, this would be in the first quadrant. Okay, so I would come over 1 and up square root of 3. So this distance would be the square root of 3, and this distance would be 1. So to find my r, which is the radius I would come out, I could use Pythagorean theorem. And I also need to find the angle in which I would sweep out and then come out that distance of r. So to find the r, we're just going to use Pythagorean theorem. So 1 squared plus the square root of 3 squared is going to give me my r squared. So r is going to end up being 2. Then to find the angle, I can use inverse tangent. Tangent is opposite over adjacent, so that would be the inverse of square root of 3 over 1, which is just square root of 3. And that would give me 60 degrees. So my point in polar form would be 2 and 60 degrees. Or you can put it in terms of radians if you want to write it as pi over 3. So that means I would sweep open 60 degrees and then come out a distance of 2. Okay, for part B, this is my xy point, and we want to change this to r theta. I don't want to move horizontally. My x is 0, and I just want to move down on the y-axis to negative 4. So this point really doesn't take a whole lot of calculations because that's right on the axes. So if you notice, if I swing open to 270 degrees and I come out 4, then I've got my point. So this one, you can just visually check it and say that my radius is 4 and my angle is 270 degrees. Part C, if I graph this is going to be in the second quadrant. I'm going to come out negative 2. So I'm coming out this way a distance of 2. And I'm going to go up 2. And I want to find my radius, and this is my angle. So I can find my r by doing Pythagorean theorem. So that gives me 4 and 4 is 8. So r is going to be the square root of 8, which is 2 square roots of 2. So that's my r, and then I can do inverse tangent by taking opposite over adjacent. So if this is my angle, my opposite is 2 and my adjacent is 2. So I've got 2 over 2, which is 1. And when I do the inverse tangent of 1, I'm going to get 45 degrees. However, we are in the second quadrant. So we have to make sure that we have the correct angle. And this is why it's important to recognize what quadrant you're in. So when I do inverse tangent of 1, that's telling me that this angle that I highlighted in red is 45 degrees. So if I take 180 and subtract 45 degrees to find out what that angle is, or I could take 90 degrees and add 45, either way I'm going to get the same thing. I'm going to get that my angle is 135 degrees. So it's really easy to just stop and say, okay, my angle is 45, when really it's 135. It is so important to recognize what quadrant you're in. So my r is going to be 2 square roots of 2, and my angle is going to be 135 degrees. So now I can check it by saying I'm going to swing open 135 degrees and come out 2 square roots of 2. And that's going to give me the same as if I was sitting on the xy plane and I came out on the x-axis -2 and up +2 on the y-axis. And the last example, this one is also easy to just eyeball it without having to worry about doing much calculations. This is telling me I'm coming out 5 on the x-axis. So this is my y and x. I'm coming out 5 on my x-axis, and I'm not making any vertical change. So that would be an angle of 0 degrees. I'm not sweeping open at all if I'm looking at it in terms of the polar coordinate plane. So if this is my x and this is my y, my radius, when I change it to polar form, is going to be 5, and I'm not sweeping open at all. That would be 0 degrees. So now we're going to start practicing converting back and forth from rectangular form to polar form with equations. And then once we get comfortable with that, we're going to actually start plotting equations in polar form in the next section. Now, most of the time, when we're looking at an equation in rectangular form, it's usually y equals and then something in terms of x. When we're doing this in polar form, we want to solve it for r. We want to have r equals and then everything else in terms of theta. Now, just like rectangular form, there are cases where you're not going to have y equals, but most of the time it will be solved for y. So, for example, we have the special case where we have a vertical line where it's actually x equals. There are times where it's not solved for y, but most of the time it is. And that is the same case with polar form. The majority of the time we're going to solve it for r, but there are cases where we don't solve it for r, special cases. So what you need to keep in mind when you're transferring this from rectangular form to polar form, keep in mind that x is r cosine theta and y is r sine theta, because the majority of the time we're just going to substitute those expressions in for x and y and then clean up the equation and try to solve it for r. So in part A, everywhere I see x, I'm going to replace it with r cosine theta. So I have 3 times r cosine theta, and y is r sine theta, and that's equal to 6. Now we want to try to solve this for r, so I'm going to factor out an r, and I have 3 cosine theta minus sine theta is equal to 6, and then I can divide both sides by 3 cosine theta minus sine theta. And now we have this in polar form solved for r. Now, when I look at this in rectangular form, I recognize that that's just a linear function. It's just a line. So when I go to graph this later on the polar coordinate plane, I should get the same picture. I should get a line. So keep that in mind as we're going through, because this is going to come up in the next section when we start graphing these equations. Okay, same thing for part B. This is a line. So when I solve this for r, and I put it in polar form and I solve for r, and I go to graph it in the next section, that equation should also be plotting the same line. It's just going to be written in a different form. So I'm going to replace my x with r cosine theta plus r sine theta is equal to 7. I'm going to factor out the r, and I'm left with 3 cosine theta plus sine theta is equal to 7. And then I'm going to divide both sides by 3 cosine theta plus sine theta. And I get that r is 7 over 3 cosine theta plus sine theta. So this should also be a line later on in the next section when we graph it. Okay, in example C, we have an equation of a circle. Oops, that should be an equal sign, not -1. Go ahead and fix that. So this is the equation of a circle with the center 0, -1. And we are going to write this in polar form. So the first thing I'm going to do is FOIL the y plus 1. I'm going to square it. So that gives me y squared plus 2y plus 1 is equal to 1. So I took y plus 1 times y plus 1 to get y squared plus 2y plus 1. And I brought everything else down. I can cross off the 1's because if I subtract 1 from both sides, those disappear. So I'm left with x squared plus y squared plus 2y is equal to 0. You should be aware, and I'll make a side note over here, x squared plus y squared is equal to r squared. We've seen that before, except typically we use r as 1 when we're talking about the unit circle. So this is the equation for any circle that has the center 0, 0, where r is the radius. So we've seen this equation before where we write it like this because our radius is 1 when we're talking about the unit circle. But in general, a circle with the center 0, 0 has the equation x squared plus y squared is equal to r squared. So this is another important equation that you need to know. So I can replace the x squared plus y squared with r squared because of my equation of a circle with center 0, 0. So I'm left with r squared plus 2y is equal to 0. So now I have to substitute r sine theta in for that y. So now we see no more x's, no more y's, and this is written all in terms of r and theta. Now we want to solve this for r. So what I'm going to do is I am going to subtract 2r sine theta from both sides and then divide both sides by r. So I'm left with r is equal to -2 sine theta. Now typically we have to be careful when we're dividing by a variable because we want to make sure that r is not equal to 0. We don't want to divide by 0. But since we know in this case that we're talking about the radius, and the radius is definitely going to be bigger than 0, that we can divide by r. So my final equation in polar form is going to be r is equal to -2 sine theta. So if I graph this, or if I graph this, I should get the same picture. It's just written in two different forms. And this is the equation of a circle. So a similar example to practice, we've got x minus 2 squared plus y squared is equal to 4. This is the equation of a circle in rectangular form with the center 2, 0 and a radius of 2, because this can be written as 2 squared, which is my r squared. Okay, so I'm going to square my x minus 2. So I have x minus 2 times x minus 2, which gives me x squared minus 4x plus 4, and then I bring down the plus y squared is equal to 4. If I subtract 4 from both sides, those disappear. And so I'm left with x squared plus y squared, and a minus 4x is equal to 0. The x squared and the y squared, I can replace that with r squared. And I'm left with minus 4x is equal to 0. And now all I have to do is replace that x with r cosine theta. And I'll have everything written in terms of r and theta. Now to finish solving this for r, I'm going to add 4r cosine theta to both sides. And then I'm going to divide both sides by r. So I get r is equal to 4 cosine theta. So this is also the equation of a circle. If I graph 4 cosine theta, or if I graph x minus 2 squared plus y squared is equal to 4, either way, I should get a circle with the center 2, 0 and a radius of 2. Okay, now we're going to practice converting an equation that's in polar form into rectangular form. So now our equations are given to us in r's and thetas, and we're going to change them into x's and y's. In example A, this is a circle with a radius of 8, and we're going to change this into rectangular form with x's and y's. So the first thing I'm going to do is I'm going to square both sides. So I have r squared is equal to 8 squared. And then r squared, as you know, is equivalent to x squared plus y squared. So I'm going to replace that r squared with x squared plus y squared. And I can rewrite that 8 squared as 64. And so now we have a circle and with the origin at the center and a radius of 8. We can do the same thing for part B. When we have r is equal to some number, that's going to be a circle with the center at 0, 0. And so we're just going to square both sides. And then I can replace r squared with x squared plus y squared. And so now we have our circle with the center 0, 0 and a radius of 4. And if you'd like, you can rewrite that 4 squared as 16. For part C, this is actually a line. If we swing open to 3/4 pi, that would be right here. Notice that there's no r in this equation. So r can be anything, which means I can come out 1 unit from the center, I can come out 2 units from the center, 3 from the center, 2.5. I can come out -2, -4. I can come out anywhere I want from the center if I swing out 3 pi over 4, which gives me this line that passes through the origin. Now, the trick to figuring out what that line is, if you don't recognize it, is I'm going to take the tangent of both sides. I can do anything I want as long as I do it to both sides of the equation. The tangent of 3 pi over 4 is -1. And tangent, when we write it in terms of x's and y's, is y over x. So now, to solve this for y, I'm going to multiply both sides of the equation by x, and I get the line y is equal to negative x. And even though it's not written in there, r plus b, which is the y-intercept, is 0. So it passes through the origin and has a slope of -1, which matches this picture exactly. So this is the equation in rectangular form, and this is the equation in polar form. Now for part D, we don't actually even have to do any calculations, because if I graph theta is equal to pi over 2, we can just eyeball this one. If I open to pi over 2 and I come out from the center any value of r, it could be anything in either direction, this is just the vertical line x equals 0. Now, if you didn't recognize this line as x equals 0, you can use a similar trick that we used in part C. If I took the tangent of both sides, I would get tangent of pi over 2, and I would rewrite tangent as y over x. But tangent of pi over 2 is actually undefined. So we can't use tangent. So then I would go back and I would try cotangent. You want to try either tangent or cotangent when you've got theta is equal to and then some angle. So if I try cotangent of both sides, I would write cotangent as x over y, and cotangent of pi over 2 is 0. And then like before, I would cross multiply, so I would have x times 1, which is x, and y times 0, which is 0, and I would get the same thing whether I noticed it by eyeballing it and just visually checking it, or whether I used a trick of taking tangent or cotangent of both sides. Okay, for part E, we have r is equal to -2 secant theta. Since I know secant and cosine are reciprocals, I'm going to rewrite this as -2 over cosine theta. And the trick here is to notice that if I cross multiply, I'm going to get r times cosine theta is equal to -2. Using the fact that I know that x is equal to r cosine theta, I can replace r cosine theta with x. So this also is a vertical line. Part F is very similar. I know that cosecant is the reciprocal of sine, so I'm going to rewrite this as 4 over sine theta, and then I can cross multiply, and I have r sine theta is equal to 4, and I know that r sine theta is equal to y. So I can replace r sine theta with y, and I get the horizontal line, y is equal to 4. So this is the same line as this, although it's in rectangular form. In example G, this is actually a circle in polar form, but it doesn't have the origin as a center, so it's been shifted. So what I'm going to do is I'm going to multiply both sides of the equation by r. So I get r squared is equal to 10r sine theta. I can rewrite r squared as x squared plus y squared. I'm going to replace the r sine theta with y, so I have 10y. Now I'm going to subtract 10y from both sides. And now I can complete the square to find the center of my circle. So let me move this 0 over a little bit so I can leave a blank on both sides since we're going to complete the square. So I take half of 10, which is 5, and square it. So I add a 25 here, but what I do to one side, I have to do to the other. So I add a 25 on the right-hand side as well. That way I keep my equation balanced. And now I have x squared plus, and I can factor this as a perfect square, so that would be y minus 5 squared is equal to 25. So now I can see that this is a circle with the center 0, 5 and a radius of 5, because this is equal to 5 squared. That's your r squared. So if I were to graph this, and I were to graph this, I would get the same picture, a circle with a radius of 5, but the center has been shifted from 0, 0 to 0, 5. Okay, let's do another one like that in part H to practice. This is a circle. We are going to multiply both sides of the equation by r. That way I have x squared plus y squared is equal to, and I'm going to replace that r cosine theta with x, so I get 12x. Then I'm going to subtract 12x from both sides, keeping my x's together, and I'm going to leave a blank here because I'm going to complete the square. Okay, so I take half of 12, which is 6, and square it, so that's 36. And what I do on one side, I'm going to do on the other side. So I have to add 36 on the other side as well. So now I can factor my perfect square, and I'm going to have x minus 6 squared plus y squared is equal to 36, which I can write as 6 squared. So now I can see that I have a circle that has a center 6, 0. So it's been shifted from 0, 0 to 6, 0, and my radius of the circle is 6.